So today we're talking about the impact that a scale factor has on perimeter, area, and volume. First, let's talk about proportional change. Proportional dimensional change means that each dimension changes by the same factor. So let's say I've got this rectangle. Maybe one side is 2 and the other side is 4. A proportional change occurs when I multiply all of the dimensions, so the 2 and the 4, by the same scale factor. I'm using a letter K to represent that scale factor. Let's say that in this case that our K is 3. So 2 times 3 is 6 and 4 times 3 is 12. And what happens when I multiply by the same factor, the length and the width, is I get similar figures. A proportional dimensional change is always going to result in similar figures. So here's an example where all of the sides of my triangle doubled in length. That was a proportional change by a scale factor of 2. And here's a second example that's also a proportional change, but in this case, my triangle got smaller. Each side was multiplied by a scale factor of 1/2. So a non-example might be where I take a square like this one. Right now it has a side length of A, and I multiply the top by 3, and then I multiply the sides by 1. So that's non-proportional because I have 2 different scale factors. So my rectangles are not similar there. So here's again our definition. Each dimension of a figure changes by the same factor. That's proportional change. Here's an illustration of proportional change. So all of the sides were multiplied by the same scale factor, and in this case, that scale factor is 2. By contrast, with non-proportional dimensional change, the dimensions of a figure change by different factors. So here's an example where I doubled the side lengths that were originally a length M, and I tripled my bottom side. So this resulted in triangles that are not similar. I did not have the same scale factor for all of my sides. Here's another example of that. So here the top and bottom length doubled, but the width didn't change. So this resulted in non-similar parallelograms. So what if we doubled the length of a figure and tripled the width? Obviously this is non-proportional because we have different scale factors. Let's think about what would happen. Here's some space to try it out. Why don't you pause the video and see what you think would happen? Hit play when you're ready to find out. Well, my new width would be 24 and my new length would be 10. So let's see how this would affect our area and our perimeter of our rectangle. Well, originally we had a width of 8 and a length of 5. So the original area would have been 8 times 5, or 40. The new area is going to be 24 times 10, or 240. So what happened? Did it double? No, then it would only be 80. Did it triple? No, then it would only be 120. We actually increased our area by a factor of 6. Where do you think that 6 came from? Here it is. 2 times 3 is 6. And that's where our scale factor came from for this non-proportional dimensional change. Now what about the perimeter? Will it do the same thing as the area? Let's find out. What about our perimeter? It also didn't double or triple. Honestly, it's not even a very pretty scale factor. The scale factor that maps our old onto our new is 68 over 26. I mean, I guess you could make it a little prettier, but it's still not something like 2 or 3, and that's because this is non-proportional dimensional change. So our old perimeter was 26 and our new perimeter was 68, and both the 2 and the 3 influenced that. But since we didn't multiply both dimensions by the same number, we didn't end up with a nice, pretty, neat little scale factor. Okay, so now we're talking about both the length and the width tripling. This is proportional because both dimensions are going to be multiplied by the same scale factor. Try it out. See what happens in this case. Remember, this time you're multiplying the width by 3 and the length. So we already found our old area. Our new area is going to be 360. So what factor did we multiply by this time? Well, 40 times 9 is 360. Where do you think that 9 came from? That's right. 3 times 3 is 9, and we had a scale factor of 3 for both dimensions. So that's where that scale factor came from. Now let's look at the perimeter. Our old perimeter was 26, and our new perimeter is 78. So our scale factor for our perimeter, the number that we can multiply the old one by to get the new, is 3. because 26 times 3 is 78. Much prettier than last time, huh? That's because we multiplied both dimensions by the same number, and that number was 3. Another thing to think about here, we haven't really been labeling our units, have we? But we know that area is measured in units squared and perimeter is just measured in units, because area is talking about flat two-dimensional space, whereas perimeter is talking about length. We don't normally write an exponent with just units, but it would be to the power of 1, right? That's one-dimensional. So an interesting thing to note here is that 9 is equal to 3 squared. We multiplied by 3 twice. And of course 3 is just 3 one time. That's a pattern that's going to occur when we're talking about proportional change. Okay, so it's your turn to make a conjecture. That means you're going to make a prediction. The length and the width and the height of a rectangular prism all triple. What happens to the surface area and volume? Think about it for a second. And now here's an opportunity to try it out. So I'm going to start out by finding the original surface area and volume of this prism. I'm going to use the bottom face as my base. So that means my perimeter of that base is going to be 10 and the area of the base is going to be 6. And my height is 1. So the surface area of this original prism is going to be 22 square feet. The volume would just be 6 times 1, so just 6. And that's cubic feet. Okay, now let's triple all those dimensions and do the new surface area. So our new surface area is 198 square feet. So how did we get from 22 to 198? Well, we multiplied by 9. Why 9? Where do you think the 9 is coming from? Well, we have square units here, right? So what's happening is that we're multiplying by the number 3 2 times. Once for the length and once for the width of each face of our object. So our scale factor is our original scale factor squared. So since we multiplied by 3 squared for our area, what do you think we'll be multiplying by for our volume? So our new volume is going to be equal to 54 times 3, which is 162 cubic feet. And it just so happens that 6 times 27 is 162. So why 27? Well, that would be because 3 cubed is 27. So this time we multiplied by our scale factor of 3 to the power of 3. So take a moment to think about this. What happens to the surface area of a 3-day solid in a proportional dimensional change? What about the volume? May as well think about the perimeter too while we're at it. Well, let's say that we changed all of the dimensions by a scale factor of k. Our perimeter would change by a scale factor of k. Our surface area would change by a scale factor of k squared. And our volume would change by a scale factor of k cubed. Now remember, this pattern is true for proportional dimensional change. It's not true for non-proportional dimensional change. For non-proportional, you just have to look at each of the different dimensional changes and figure out what's going on. But this is a pretty cool pattern for when you're working with proportional change.